Now, in terms of picking up where we left off, okay, and we looked into multiplicity, and on page 266, okay, now the other day, okay, we looked into writing polynomials in expanded form as well as factored form on the basis of given zeros and multiplicities, and we finalized in the case of taking what we had with an expanded polynomial and writing in factored form, and from the factored form we looked at the determination of the zeros and their multiplicities. And again, multiplicity of a zero will be in reference to the degree to which the factor that corresponds to that zero is going to be raised. And now for what we have on page 23, okay, so you have a given function, and we have this one provided in expanded form. So we have f of x is equal to x cubed plus 2x squared minus 25x minus 50. Okay. All right, so we have a polynomial, okay, that is an expanded form, and looking at what we have in the mix. Okay, now, not all polynomials, in fact, most polynomials will not be factorable in the context of taking a factoring by grouping setup. But for what we have here, now we have the expressions in x going down 1 degree at a time, and also for the coefficients, okay, we have relative to what we have interacting between the second and first terms. So you have second term has a coefficient of 2, first term has a coefficient of 1. So you have like a 2-to-1 ratio. And also with the last two terms, you have the coefficients negative 50 and negative 25. Negative 50 to negative 25 is also a 2-to-1 ratio. And for what we have here, okay, I'll be able to, because the way that the degree of the terms is expressed, and also with the way that the coefficients will be aligned, I can perform factoring by grouping. And in this one, okay, so we have for x cubed plus 2x squared, okay, if I group together these terms in parentheses, okay, so I have the quantity of x cubed plus 2x squared, and I have separating, okay, I have the operation of subtraction, so separating the first two terms apart from the last two terms. Okay, so I have a negative, and if I factor out, okay, the subtraction, or in this case negative 1, so you have for minus 25x, okay, that is going to be the opposite sign of 25x. And for what we have in the case of negative 50, we have the opposite sign of 50. And looking at what we have in the groups, okay, so we have with x cubed plus 2x squared. Okay, now the greatest common factor between these two terms will be x squared, and taking into x cubed plus 2x squared, so we have the quantity of x plus 2, and once again bringing down the subtraction, okay, so you have minus, now for 25x plus 50, okay, greatest common factor here is going to be 25, and taking 25 into 25x plus 50, we're going to have x plus 2, and so we're going to have a shared binomial factor with x plus 2. And the other factor at this stage, we're going to have clustering together, okay, the outside terms in operation. So we're going to have x squared minus 25 and x squared minus 25, okay, we're going to have a difference of squares. Okay, so I have x plus 2, and with x squared minus 25, okay, so this will factor to x plus and x minus 5. Okay, and I'm just going to rewrite this. So this is going to be the factored form. And I'm going to stress the degrees for each of the factors. Okay, so you don't see any exponents for any of these factors. Okay, so if you don't have anything explicitly written, okay, we have we just regard each of the factors as being raised to the first power. Okay, so we have, in the case of the zeros, okay, so you have from x plus 2, if I set x plus 2 equal to 0, okay, so I have x is equal to negative 2, okay, and we have with the first degree, okay, so you have the multiplicity is equal to 1. And we have from x plus 5, we have x is equal to negative 5. And because that factor is raised to the first power, okay, we have that multiplicity is also equal to 1. And we have, once again, okay, with x minus 5, okay, we have the remaining 0 at 5. And because the corresponding factor, which we have x minus 5, since that is of first degree, okay, 5 is going to have a multiplicity also of 1. Okay, so this is what we have within the framework. Okay, so we have, again, we have, for this polynomial, I was able to factor by grouping, and upon doing so, I wound up with 3 binomial expressions, okay, in the complete factorization, from which we have to bring forth 3 distinct zeros with negative 2, negative 5, and 5. And again, because each of the binomials is a first degree, okay, all the multiplicities of the zeros we have to be at 1. All right, now for what we have in the case of number 28, okay, this time we're going from the function f of x to n of x. And we have n of x, okay, so you have x to the 6th plus 4x to the 5th. And we have plus 4x to the 4th. All right, so looking at factoring, okay, all of these are variable terms of a higher degree, okay, and for x to the 6th, 4x to the 5th, and 4x to the 4th, okay, now we're going to have a greatest common factor to pull out, okay, so in this case we're going to have x to the 4th, and taking into the trinomial, so we're going to have x squared, and we have plus 4x plus 4. And for what we have here now, x squared plus 4x plus 4, okay, that is going to be a squared trinomial, meaning that once I factor, I'm going to have the same binomial to appear. Okay, so you have x plus 2 times itself, and this is going to appear twice. And for what we have in the case of n of x, this is equal to x to the 4th, and we have times x plus 2, which is going to be raised to the 2nd. Okay, so we got in the factor form, so we have x is going to be raised to the 4th, and we have x plus 2, which will be raised to the 2nd. And in the case of what we have in the zeros, okay, so from x to the 4th, okay, so if you have just the monomial x and you're not adding or subtracting anything from this, okay, we're going to have the x is equal to 0. And because x is to the 4th power, okay, we have that the multiplicity is equal to 4. And from x plus 2, if I set this equal to 0, okay, I have the other 0 value to be at negative 2. And because x plus 2 is squared, okay, negative 2 is going to have a multiplicity of 2. All right. Now, in the case of what we have for the next item, okay, and we have for number 29, okay, and this function, okay, we have in p of x, and this is already going to be laid out in factored form. So here we're going to have p of x is equal to negative 3 times x, and we have times x plus 2 raised to the third, and we're going to have times the quantity of x plus 4 and so just okay, so we had the factored form already. Now in the case of what we have in the zeros, okay, so you got negative 3x at the front. Okay, so since we're looking at zeros and multiplicities, okay, so just the standalone x, okay, that is a first degree for x plus 4. Okay, we can regard that as also as being a first order. And now we have with the variable factors. So negative 3 is not going to do anything for us in terms of determining the zeros or multiplicities. It's just a coefficient. So in other words, if I had just x plus 2 cubed and x plus 4, I'm still going to have the same zeros and multiplicities. So for just the x alone, okay, we have from this, okay, we have x is equal to 0. And we're going to have that the multiplicity is equal to 1. And from x plus 2 to the third. Okay, so I have x is equal to negative 2. And again, for the multiplicity, we have the corresponding factor to be raised to the third power. Okay, so we have the multiplicity equal to 3. And then we have for the remaining 0, we have x is equal to negative 4. Okay, and from this, okay, we're going to have a multiplicity of 1. Okay, now, in the case of what we have with number 30, okay, so we're going to have a function q of x. And this is also expressed in factored form. So we have negative 2 times x to the fourth. And we have times the quantity of x plus 1 raised to the third. Okay, and we have times the quantity of x minus 2 raised to the second. All right, so we have q of x, just like p of x, is expressed in factored form. So we have with our variable factors, so we have x plus 1, and x minus 2. So we have with the first of the zeros. Okay, so we're going to have x is equal to 0. And with x to the fourth power, have the multiplicity is equal to 4. And from x plus 1, okay, we have x is equal to negative 1. And because x plus 1 is raised to the third power, we have the multiplicity equal to 3. And with x minus 2, okay, we have x is equal to 2. And since the corresponding factor, x minus 2, is raised to the second power, we have that the multiplicity is going to end up at 2. All right. Now, in the case of what we have with number 38, okay, this one, it's going to be a bit of an outlier in comparison to the previous problems. Okay, and in 38, now we have the function. We have m of x. And in the case of m of x, okay, this is set equal to x to the fifth minus 5 times x to the third. And for what we have in the case of m of x, now both of these are terms in the difference, okay? We have the variable x present. Now we have for the greatest common factor, we're going to have x to the third. And factoring out x cubed, okay, so we're going to have x squared minus 5. And this is where the outlier comes in. I'm going to factor this out, okay, but now 5 as an integer is not going to be a perfect square. At least it's not a perfect square in the whole numbers. But just factoring this out, okay, so for x squared minus 5, okay, so you have a difference of squares. Now from x squared, I'm going to have x and x. Now in terms of 5, okay, in terms of perfect squares, now 5 is just going to be the perfect square of the square root of 5. And with the difference of squares, it's going to have plus the square root of 5, as well as x minus the square root of 5. So this is an outlier because from the start, we've been looking at factoring out integer coefficients. And this time, okay, we have this particular string to be broken thanks to this last problem. Okay, and so in both of these factors, we have a first degree and for what we have in the case of the zeros, okay, so you have the x is equal to 0. Okay, so you have the multiplicity is equal to 3. From x plus the square root of 5, okay, if I set this equal to 0, so I have x is equal to the negative of the square root of 5. And since this corresponding factor is a first order, we have the multiplicity is equal to 1. And as for x minus the square root of 5, if I set this equal to 0, so I have that x is equal to the square root of 5. Okay, and so we had that multiplicity is equal to 1. All right, and tell you what, we'll look at some of the dynamics that are carried out in terms of graphing. But I tell you what, just for the next few moments, okay, let's see what we get. See, we have here, like in determining the zeros and multiplicities. We'll say that between the functions, okay, we'll say for the first one, okay, we'll say we have f of x is equal to 2x to the fourth plus 4x cubed plus 2x squared and for the second function, let's see what we get for the zeros and multiplicities. Okay, for f of x is equal to x to the sixth plus 10x to the fifth plus 25 times x to the fourth. So let's see what we get for the zeros and multiplicities for these two functions. Okay, for what we have in these exercises, okay, so looking for the zeros and the multiplicities. Okay, so we have for the first function, okay, so you have f of x is equal to 2x to the fourth plus 4x cubed plus 2x squared. Okay, and now looking at factoring. All right, so we have all the terms have an even valued leading coefficient. So we have so we got 2x to the fourth, 4x cubed, and 2x squared. And the last of these terms is going to turn out to be the greatest common factor. So we have 2x squared, and taking into 2x to the fourth plus 4x cubed plus 2x squared. So I'm going to have x squared plus 2x plus 1. And we have here a squared trinomial. So here we're going to have f of x is equal to 2x squared, and with x squared plus 2x plus 1, so we have x plus 1 times itself, and since x plus 1 appears twice, we're going to put the factored form in the compact notation. So we have 2x squared times what's going to be x plus 1 raised to the power to which it appeared, number of times it appeared in the previous step. So that's going to be to the second. All right, so you have 2 times x to the second times the binomial x plus 1, which is also to the second. Now we're going to have with the zeros. Okay, so from 2x squared, the variable factor we had to be at x. So from x, we have x equal to 0. And since x is squared, okay, the multiplicity is equal to 2. And for x plus 1, if I set this equal to 0, I have x is equal to negative 1. And since we have x plus 1 raised to the second, we have that the multiplicity is equal to 2 as well. All right, now in this other case, now we have a sixth order polynomial that is written in expanded form, and just taking what we have here. So we have f of x equals x to the sixth plus 10x to the fifth plus 25x to the fourth. And for what we have throughout, okay, now we have x terms, and the greatest common factor, okay, that is going to be x to the fourth. And factoring out x to the fourth, okay, we have left over, we'll have x to the second plus, and x to the fourth will go into 10x to the fifth, 10x times, and x to the fourth into 25x to the fourth. Okay, this will go 25 times. And as a bit of partial history repeating, okay, we have the trinomial that is factored is also going to be a square. Okay, so here we have with x squared plus 10x plus 25. Okay, this is going to factor to x plus 5 times itself. And so just writing in compact notation. Okay, so we're going to have x to the fourth times what is going to be the square of the binomial x plus 5. And so we're going to have, in the case of the zeros, okay, so from the x factor, we have x is equal to 0. And since the x factor is raised to the fourth, again, we're going to have that the multiplicity is equal to 4. And as for what we have for x plus 5, okay, we have the x is equal to negative 5. And since we have the square of x plus 5, okay, we have that the multiplicity is equal to 2. All right. Now, in looking at what we have in the lead up, okay, to what will exist in the graphing, and where we're going to have the multiplicities to be of some level, or at least in terms of graphing. This is where the multiplicities will have a role of significance. And we have, in the case of graphing, we have in graphing, okay, so you're going to have f of x. If it has zeros, okay, it's going to do any of two things, and it might be doing a blend of both. And for what we have in the case of f of x, okay, now f of x is going to cross the x-axis at zeros of odd multiplicity. Okay, so again, just to stress, in case you have crossing the x-axis at zeros of odd multiplicity. Okay, now for the other zeros, now f of x is going to, instead of crossing, it's just going to touch or like bounce off the x-axis. So it's going to touch the x-axis at zeros of even multiplicity. All right, and to give you a bit of a visual example, okay. Okay, say we have a function, and we'll say we have f of x is equal to x plus 2 to the fourth. Times the quantity you have x minus 3 to the second. And we have times x minus 6 to the second. And we have times the quantity of x minus 10 raised to the third. Okay, so if I were to identify, let's say, the zeros, and the multiplicity, and in terms of whether it's going to cross or touch the x-axis, and I tell you what, I think what I'm going to do here is to do a little bit of color coding. Okay, so I just want to stress, okay, so for multiplicities, okay, so you have these factors laid out. Okay, so multiplicity would be like the degree to which each of the factors will be raised. Okay, so you have multiplicity of 4. Okay, so we're going to have 4, and 4 is an even value, so the graph is going to touch And the next multiplicity, okay, so we have it 2. 2 is an even value, so that's going to touch. Next multiplicity have to be 2. Okay, so that location is going to touch. And with the third degree, okay, so you have 3 as the multiplicity. That is an odd value, so it's going to cross. Okay, now for the zeros, okay, so you got your factors, x plus 2, x minus 3, x minus 6, and x minus 10. Okay, so you got x is equal to negative 2 from x minus 3. I have x is equal to 3. From x minus 6, I have that x is equal to 6. And with x minus 10, if I set this equal to 0, so I'm going to have the x is equal to 10. Okay, and okay, so for the activity, okay, so again, negative 2 has a multiplicity of 4. So the function f of x is going to touch at x is equal to negative 2. And then with 3 with the multiplicity of 2, it's going to be at x equals 3 that the graph is also going to touch the x-axis. And with 6, since that has an even multiplicity, so this is going to touch at x is equal to 6. And we have with 10, which has an odd multiplicity value, so this graph is going to cross at x is equal to 10. Okay, so just for the general layout on this one, they're just doing a bit of a quick sketch. Okay, so we have our 0 values. So you have 1, negative 0, at negative 2. Okay, we have 3. And we have 6. And also we have x is equal to 10. Okay, and in terms of the activity that we have regarding f of x, so I'll just go ahead and plot the intercepts. And for what we're going to have in this particular case, all right, so we're going to have at negative 2, okay, so just using t for touch, c for cross. Okay, and in terms of what we have for the activity, okay, I'm not going to graph this according to scale by any stretch of the means, but just want to mention, okay, so now the graph of f of x is going to start below the x-axis, and it's going to rise toward the x-axis, and once we get to negative 2, instead of crossing, it's going to touch. So the graph is going to bounce beneath the x-axis, and then it's going to rise again. Once we get to x is equal to 3, it's going to touch, so it's going to bounce off. And once we get to x is equal to 6, it's going to bounce off once again. And once we get to x is equal to 10, okay, the graph is going to cross the x-axis. So that would be the nature of the graph for what we have for this particular f of x. Now, I'm not drawing this according to scale, and it might be that the relative minimum between 3 and 6 will actually be lower than what I have near the y-axis. But I just wanted to show you, so you have, so you got touch at x equals negative 2, touch again at x equals 3, touch again at x is equal to 6. But once we get to x is equal to 10, okay, the rest of the graph of this function is going to be above the x-axis. And one might ask, okay, how did I know that the graph started below the x-axis and finished above when it might have been the other way around? Well, there is a key key set of details that we have that is going to define what we have in the case of the end behavior of the graph of a function. And in the case of the end behavior of the graph of a function. Okay. Okay. See, we have for a polynomial f of x. Now I'm going to start out with general theoretical notation and like with superscripted and subscripted variables. So you have for a polynomial function, so you have a of n x to the n. Let me stress this too, for a polynomial in descending degree order in x. Okay, so you have f of x, you have a of n x to the n plus a of n minus 1 times x to the n minus 1. And we have plus a of n minus 2 times x to the n minus 2. And you have going all the way down to, okay, and you're going to have, like symbolically, you're going to have a of 0. And that a naught, that's just going to be a constant, a number. It could be 0, it could be a negative value, it could be a positive value. But the a naught, you don't have any x beside it. Okay, so that's just going to be a constant. Whereas the terms before this will have at least a degree in x. Okay, so for a polynomial, okay, now the term that will be focused upon, okay, we have with a of n x to the n. And we have, in this particular case, right, so a of n, that's going to be the leading coefficient. Okay, and for what we have in n, that's just going to be the degree of the polynomial. And there will be scenarios drawn out, okay, and this is where the end behavior comes out. And we're going to have 4 distinct cases. And I'm going to take kind of like a little bit of a grid or pattern. Okay, say we have, first of all, okay, say we have that a of n, okay, the leading coefficient, okay, say if this is positive, and the degree to which n is raised is going to be an odd value. The end behavior here is going to be, okay, now the Alex terminology would be like falls to the left, rises to the right. And in just a little bit shorter terminology, you have down to the left and up to the right. Now, let's say that if we have the leading coefficient to be negative, and we have that n is odd, okay, you're going to have the polar opposite. Okay, so if the leading coefficient is negative and the power is odd, we're going to have for the n behavior, okay, we're going to have up to the left and down to the right. And let's say that if we have changing up here, so if we go back to where a of n is positive, and we have n to be an even value, okay, and this is going to be like a case to be like what we just dealt with quadratic functions. Okay, so you have like a of n, your coefficient a, if it is positive, then the graph is going to rise upward from the vertex, and it'll be both halves of the parabola will be going up. So both ends you have up to the left and up to the right. And we have just remaining case here. If I have that a of n is negative, while n is even, okay, and it could be like a quadratic function with a being a negative. So the n behavior, you have opening downward, so you have down to the left and down to the right. Okay, so this is going to be kind of how things are going to follow through, okay, regarding the n behavior. And let's say that if we have so if you have, like in the case of determining n behavior, and we'll say we have for the first function, we'll say that we have f of x is equal to, and we'll say we have 2x cubed plus 1. Okay, so you don't have any square or first order x terms, but for f of x is equal to 2x cubed plus 1. Okay, so the highest or the higher degree term is going to be 2x cubed. So just kind of since I'm comparing two terms, it really should be a higher degree term, but it's the same effect. So the higher degree term, okay, we have at 2x cubed. And again, the significance, okay, so the leading coefficient, okay, we have a of n, and a of n is going to be in reference to 2. And 2 is positive. And again, just for the degree itself, okay, that's defined by 2x cubed, where x is to the third power, so n is equal to 3. So this is going to be an odd value. So we have, in the case of the end behavior, okay, so if you got a positive leading coefficient and the degree is odd, the end behavior is going to be down to the left and up to the right. Or falls to the left and rises to the right. Okay. And I'm just going to do kind of a quick sketch on this one. Okay, so for 2x cubed plus 1, so once we get to x at 0, so you have like the point 0, 1. Again, I'm not drawing this according to scale. Okay, we have f of x is equal to 2x cubed plus 1. And again, we have with the end behavior. Okay, so you have down to the left and up to the right. And say we have, see another case here. If I have f of x is equal to, and I'll kind of do a little bit of a jumbled array on this one. Say if I have like 1 minus 5x to the 4th plus 2x. Okay, so if you have like the terms in sort of a jumbled array, just rewrite the function where you're going to have the terms in descending degree order. So if I kind of amend this one, okay, so the highest degree term, you're going to have a negative 5x to the 4th and the next highest degree term will have it 2x. And we have plus 1. Okay, so we have in the mix. Okay, so you got, so in other words, you might have the terms in jumbled arrays. So don't always assume that what is presented at the front is going to be the highest order term. So just double check what you have in the degrees. Okay, so the highest degree term we have negative 5x to the 4th. Okay, so we have negative 5, okay, times the x to the 4th. And again, so we have with the leading coefficient. Okay, so we have a of n, that is negative 5. So that is negative, and for what we have in the case of the degree n, we have n is equal to 4. So you have a negative leading coefficient, and the power of the polynomial, okay, is an even value. So you got negative and even. So where we have negative and even, so you got, if leading coefficient is negative and the degree is even, the end behavior is going to be moving down both to the left and to the right. So you have down to the left and down to the right. And again, just for the nature of the layout, again, I'm not going to be drawing this exactly according to scale, but for what we have in this particular case. All right, so we got it's not exactly going to have symmetry like this might appear to have. Okay, but you got your graph of f of x equal to negative 5x to the 4th plus 2x plus 1. Now in terms of the form, it might look like something quite different in appearance because, like I say, I'm not drawing according to scale. However, the end behavior is still going to be the same. We have down to the left and down to the right. Okay, so we were able to attain end behavior on the basis of polynomials that were provided in expanded form. And if I give you a scenario, okay, let's say that if we have in factored form, I just kind of use as sort of building blocks here. Okay, so you have given f of x is equal to, and we'll say we have negative 2x cubed, and we have times the square of x plus 4 raised to the second. So you have negative 2x cubed times the square of x plus 4. Okay, so first of all, if I were to determine the end behavior, okay, this will probably take a little bit of getting used to, especially with the functions that are given in factored form. Okay, but for f of x is equal to negative 2x cubed times the square of x plus 4. Okay, now what's going to happen here is that for the highest degree term, in terms of taking what we have in the mix. Okay, so we have at the front, and you're going to be including the coefficient as well. So you got first factor. Okay, we have a negative 2x cubed. Now, for x plus 4 to the second. Now, if I were to take x plus 4 times itself, I would have x squared plus 8x plus 16. And the highest degree term in that trinomial would be at x squared. So for the binomials, trinomials, polynomials that are in among the factors, you're going to take the highest degree term from what is inside the parentheses. In this case, you're going to have x, and you're going to take it to the exponent to which that factor or that factor is going to be raised. Okay, so we've got negative 2x cubed and we have times x to the second. So again, we have negative 2x cubed times x squared. Okay, so taking the product, okay, so I got negative 2x cubed. In other words, I have like negative 2x cubed times x squared plus 8x plus 16. Our highest degree term is still going to be negative 2 times x to the fifth. Okay, and so from this, okay, from the highest degree term, okay, again, your leading coefficient, a of n, is going to be at minus 2. Again, this is going to be negative. And we have that the degree of the function. Okay, again, that is defined by the highest order term that is going to result. So we have n is equal to 5, and 5 is going to be an odd value. And we're going to have for the end behavior, again, just for what we have in referencing the general layout. Okay, so we had leading coefficient was negative, the degree is odd, so you have a negative leading coefficient and the polynomial degree is odd, and behavior is going to be up to the left and down to the right. So this is going to be the end behavior. Okay, now for other characteristics, okay, for this function, okay, if I determine the zeros, the multiplicities, and where f of x crosses and touches the x-axis. Okay. So we're kind of rolling back, okay, to where we started out with regarding zeros and multiplicities. So again, we have f of x. Again, we have equal to negative 2x cubed times the square of x plus 4 okay, so you have with the zeros and their multiplicity and for this one. Okay, so we have let's see. Again, it might help to go ahead and get the multiplicities out of the way. So you have looking at the exponents. Okay, so you got 3. and also we have 2, and again, the graph of a function is going to cross the x-axis at the locations where we have odd multiplicity, and the graph is going to touch where we have even multiplicity. Okay, so 3 is an odd number, so it's going to cross. 2 is even, so it's going to touch at that particular 0. Okay, and for the zeros that will correspond, so we have with the first variable factor, which we have at x. Okay, so you have x is equal to 0. And then we have from x plus 4, we have x is equal to negative 4. So I've already identified the behavior. So in terms of like where it's going to cross, okay, so it's going to cross at x is equal to 0. And it's going to touch at x is equal to negative 4. Okay. And in terms of just kind of taking a sketch of this function, and just compositing together the features from the first 2 parts. Okay, so we have with the values, the zeros. Okay, so you have 0 and negative 4. Okay, so you have negative 4 and 0. And again, at negative 4, okay, so the graph is going to touch. And at 0, okay, we have the graph is going to cross. And for what we have, again, just from the earlier part, we had the end behavior was up to the left and down to the right. Okay, so you have up to the left and down to the right. Okay, and for what we have, just kind of fill in. Okay, so you have touch at x equal to negative 4. So if I go from upper left-hand section, so you have descending to the x-intercept at negative 4. So instead of crossing, it's going to touch, and it's going to go up, and then it's going to go down. And once the graph gets to the origin, okay, it is going to cross. Okay, so this will be the dynamic of what we have for f of x. Again, is equal to negative 2x cubed times the square of x plus 4. Okay. All right, and now just something I do want to mention. Okay, this is from the other day. Going back to what we have with quadratic functions. Okay, just from the group, okay, on page 249. Okay, and this is like looking at translating what we have going from standard to vertex form. Okay, so for the standard form, okay, so we have q of x is equal to, okay, we have 2x squared minus 4x minus 3 And again, just translating from standard to vertex form. So I'm going to start out separating the variable terms apart from the constant. Okay. And now I'm going to enter the stage eventually of the completion of the square. And for the completion of the square part, again, I want the first term inside the parentheses to be x squared. So I don't want any number other than 1 in front of the x squared within the parentheses. So again, I'm going to factor out 2. So yeah, right now, so you have q of x equal to 2. And we have times the quantity of what is going to be x squared minus 2x, followed by the subtraction of 3. Alright, now where the completion of the square is going to enter the scene. Okay. So for completing the square, so the first term inside the parentheses, okay, again we have an x squared. Now with completing the square, I look at the first order x term, and I'm going to take the coefficient alongside it. Okay, so we have negative 2, and I'm going to take half of this. Half of negative 2 is going to be negative 1. And the square of negative 1 is going to be positive 1. And we have with q of x, so we have 2 times the quantity of x squared minus 2x, and we'll have the addition of 1. Right now we have the subtraction of 3, but again, I want to create a bit of a balance, because whatever I end up with in the vertex form, I want this to be exactly equal to what I have in the standard form. So if you notice right now I have 2x squared minus 4x, and if I add 1 here, I'm collectively adding 2. So you have like plus 2 minus 3, which would be minus 1. So you're not going to have a negative 3. So to offset the imbalance that is created, okay, notice as I'm completing the square in this fashion, what I'm doing in effect is that at the front, I'm not just adding 1, instead I am adding 2 times 1, which is going to be 2. So overriding the surplus that is created, I'm going to have to, at the back, take away 2. So I have for q of x, okay, so again I have 2 times the quantity of x squared plus 2x plus 1, followed by this time around, okay, the subtraction of 5. Okay, so just looking at what we have here, so I got 2x squared, and it should be minus 2x squared minus 2x. Okay, so you have 2x squared minus 4x, and you've got plus 2 minus 5. Plus 2 minus 5 goes to minus 3. Okay, now condensing what we have in the trinomial. So you have for q of x, okay, so you have 2 times. Okay, we have the square. Okay, the binomial we'll be looking into. Now your k value is already going to be at negative 5. Okay, now for x squared minus 2x plus 1. So from the x squared, I have the square of x. Now in terms of where the rest is going to come in, the number we just squared to create the completion of the square activity, okay, we had taken the square of negative 1. Okay. Okay, so to fill in and complete that binomial, okay, so you have the square of x minus 1 So for the vertex form, in this case, we have 2 times the square of x minus 1 followed by the subtraction of 5. Okay, so this is going to be the vertex form. Now, in terms of identifying the vertex, and the other characteristics. Okay, so we have, for the leading coefficient 2, okay, so we have that.
I didn't get that. Could you try again?
I'll try again. Okay, so you have this, okay, so you have the leading coefficient a, so you have a is equal to 2.
I don't understand.
Shh. So you have the a is positive. Okay, so we're going to have that q of x is going to rise upward, open upward from the vertex. Okay, and in terms of what we have for the h value, okay, so again we have x minus 1 equal to 0. We have the x is equal to 1. So you have the x is equal to h is equal to 1. And again, we have with the k value. So we have that the k value is equal to negative 5. Okay, and so we have for the case here, so the vertex hk we have located at 1, negative 5. Okay, now we had both the standard form, okay, and I had to determine the vertex form. Now, I'm going to stress this part here. You got your choice. You can use the standard form or the vertex form to get to the intercepts. Now I'm just mentioning, okay, for the x-intercepts, I'll just go ahead and mention this. Now again, it's kind of like the protocol where you're looking at solving for x as y is set to 0. Now for the x-intercepts, you're going to have some irrational roots in the mix. I'm just going to put this in coordinate fashion. Let's just go ahead and give you this result. Okay, and those numbers, okay, we had at negative 0.5810, and also we have at 2.5810. And I'll just go ahead and mention, okay, just for the follow through in the determination of the y-intercept. Again, this is very much open-ended. Okay, you could say that at the one end, if you're to take, say, with the standard form, you have like y is equal to q of 0. If I went with the standard form, I would have like 2 times the square of 0 minus 4 times 0 minus 3. And guess what? We have 0 squared is 0, minus 4 times 0 is 0, and we have minus 3. So yeah, y is equal to negative 3. So in coordinate fashion, okay, we have that the y-intercept is at 0, negative 3. And I'm just going to mention, had you chosen the vertex form, okay. So again, that was this statement here. So if I have like y is equal to q of 0, and the vertex form would be like taking 2 times the quantity of 0 minus 1 to the second minus 5. Zero minus 1 is negative 1. And the square of negative 1 is going to be a positive 1. And 2 times 1 is 2, minus 5. So regardless of whether you use the standard or vertex form, you're going to get the same intercepts, okay, for both the x-axis and the y-axis. You don't have to do both. You just have your choice of either approach. So the y-intercept, okay, so you're going to have it 0, negative 3. Okay. And now where the sketching is going to come in, just want to mention if I can. Okay, so you have at least for this particular function. Okay, so you're going to have the vertex at 1, negative 5. Okay, and again, we're going to have with the axis of symmetry, we have an x is equal to 1. So you got the vertex, and again, because the leading coefficient is positive, okay, the graph opens up from the vertex. Okay, so in this case, we have 1, negative 5, and as we go up, again, at the same y value, you're going to have your x values to be equidistant from the axis of symmetry. Okay, so you have like with the y-intercept, okay, you have this much room to the left, and the level to 0, negative 3, have 2, negative 3, also level and equal in distance from the axis of symmetry. And then we have with the x-intercepts, so you have those coordinates. And now, just want to mention, for the key details, in terms of, and we have in the remaining portions, and this was kind of reminiscent of the relative minimum, relative maximum. And we have in the case of part G, okay, so you have, again, so you had the vertex at 1, negative 5. And part G is asking for determining the minimum or the maximum. And again, the graph opens up. And since the graph opens up, the vertex is going to be the location of the minimum. And the minimum value is going to be the y value, or the second coordinate in the vertex. So the minimum value in this case, you would have that y is equal to k. Okay, that's going to be the second coordinate. Okay, and so that is going to end up at -5. And for what we have regarding the domain and the range. And we have just regarding the activity, so the domain is going to be in reference to the x values. So I'm going to do a little bit of projection on it out here. Okay, so you have to the left, you have the graph is moving slowly to the left, and then we have up and to the right, have the graph is shifting slowly to the right. And so you have continuous movement on both sides horizontally, continuously decreasing, continuously increasing, between negative and positive infinity, and you have all the real values in x throughout. So for the domain of this function, you have between negative and positive infinity. So you have the set of all real numbers. Now for what we have in the case of the range, for what we have in the case of the range, so you're looking at vertical motion. And again, so we're starting from y is equal to -5. And that's going to be the bottommost value of y. And then we have from -5, again, you have upward motion. And here we have essentially for y, the sky is the limit. And so you have y increasing on out to positive infinity on the y scale. So for the range, okay, there's no negative infinity on this one because we're not moving continuously downward. In fact, again, we had the function bottoms out at y is equal to -5. So the range you have going from and including -5, and then you have everything else greater than -5 to make up the y values in the graph of this function. So you have going from and including -5, heading on out to infinity. Okay, so the domain you had concerning the x values, everything. So you got everything between negative and positive infinity. But we have for the range, you had the y values. So you have going from and including -5 on up and reaching out to infinity.